everybody. In this lesson video, we are going to go over how to graph tangent. We'll start with the parent function, and I save it for the end. We did sine, cosine, cosecant, secant first because they all have something in common. Tangent and cotangent, while they have something in common with each other, there is a little bit of a difference that we should incorporate. So let's just dive right in, and as we create the parent function, I'll explain what's different about it and why, and what we do to adjust everything. So for one thing, y equals tan x. For starters, whenever I graph tangent, and everyone's going to kind of do it a little bit differently, I'm still going to graph between 0 and 2 pi for my parent function. However, if you think about tangent begins, and we talked about this when we were solving trig equations quite a bit. Tangent repeats its pattern much sooner than sine or cosine, cosecant, or secant do. It takes those four trig functions, the entirety of the unit circle, for your output values or answers to those trig functions, for those to repeat themselves and begin their cyclic periodic nature. Whereas tangent, the answers that you're going to get, if you consider the angles as they would be represented in standard position, the answers that you get for tangent from there to there, for instance 0 to pi, will be identical to the answers that you get from there to there, from pi to 2 pi. That means that the period for tangent is not 2 pi. Instead, the period for tangent is pi. That also means then the period formula that will be affected or impacted by A, B, H, K, well really just by B, but the period formula is going to be pi over B, not 2 pi over B, okay? That's one main difference. And we'll take it from there, and what you'll do is you're going to graph 2 full cycles, and this way it kind of levels out the window that we're analyzing these graphs on. So let's go. All right, I'm going to draw my y-axis, just like I did for my other examples, and my x-axis. Now, when we graphed sine and cosine, the range, the outputs, oscillated between -1 and 1. So we were really just worried about making sure y values could fit and we could see them really well that were between -1 and 1. When we did cosecant and secant, well, those were the reciprocal functions, so there was some reciprocal nature there, right? So all the interesting stuff for cosecant and secant, since they're the reciprocals of sine and cosine, well, those are going to be 1 and bigger, or they're going to be -1 and smaller. They're not going to be between that 1 and -1. They'll include 1 and -1, but they won't include those numbers in between. So that middle part we didn't really care about, but we really did care to see more of the graph above and below because we drew those little U-shaped graphs, right? Tangent's sort of similar. We do want to see more vertical. We want to see more of the graph up high, more of the graph down low, but we will also see graph in the middle. Tangent, as a trig ratio, tangent of theta from geometry and on, is the opposite over the adjacent. There's no rule for which of those can or cannot be the biggest or bigger side. Anything's possible. If the opposite's smaller than the adjacent, well then the ratio is going to be, and this is assuming we're only dealing with positives, okay? If the opposite is less than the adjacent, then you're going to have something less than 1. And if the adjacent is bigger, if the adjacent is smaller than the opposite, if the opposite's larger than the adjacent, the other way, top's bigger, well, now we're going to have numbers bigger than 1. And at 45 degrees, we're going to actually have answers equal to 1 because the opposite and the adjacent are equal. So 1 is where we kind of switch, cross over. So 0 is usually where you cross over from negatives to positives, right? 1 is where you switch from fractions with a smaller opposite than adjacent to fractions with a bigger opposite than adjacent. So that 1 answer, which is at the 45 degrees, or so 45, 135, 225, 315, or the pi over 4s, which is a little bit better to think of it as 1 pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. They're important. So we're going to include those and our quadrantal angles. And that is what's going to get us twice as much graph to look at. So I know this is a lot. You might have to rewind and listen to it again after we actually get the graph on the paper, and all these things will make more sense, okay? So we usually had 5 tick marks, and that was for the 4 quadrants because you need one to kind of start or finish the whole window that you're looking at. Whereas we're going to add 4 more. That makes 9. So it makes 8 spaces that we're looking at. When it comes to the unit circle, what are these spaces that we're looking at? Well, it's like a pizza, okay? So we're really looking at each slice of the pizza. Now I'm going to kind of draw my x-axis a little bit longer because I want to be able to see a little bit more detail. So think of that as a horizontal stretch in a way. So I'm stretching this out so that I kind of have a little, it's not so straight, a little bit more space to analyze what's going on over. It's going to be pretty similar to how we did the tick marks when we put 5, when we put 9. So my strategy, first tick mark and last tick mark, put 1 in the middle. It's not that precise, but okay. Middle, that's 5. If we put in 4 more tick marks, let's even add a little pizzazz. If we add 4 more, which are going to be these pi over 4 tick marks where tangent equals either 1 or negative 1, they're going to split each of the spaces we have right now. So 1, 2, 3, and 4. Count them up. So don't forget the origin. Count them up, and you have 9 tick marks, okay? Now we're going to go label them. What are we labeling them with? Well, with the angles between 0 and 2 pi, counting by pi over 4s. So when we've been doing these examples, I keep leaving everything with a common denominator. Let's kind of look at it that way. I just told you guys how the period for tangent and cotangent is pi by how it behaves. From here to here, the outputs that we get, even if you only consider the special angles, obviously you could take the tangent of 1 radian, 0.1 radians, there's more, pi over 10, pi over whatever, there's angles everywhere. We just focus on pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, pi, and so on. Those are special angles, multiples of pi over 6 or pi over 4, also known as 30 degrees and 45 degrees. But the formula needs to include if this b value, which is 1 by default, isn't a 1. So the period is pi over b as a formula. This right here is actually the same as 1 tan 1 x minus 0 close plus 0. So a and b are both 1. H and k are both 0. Okay? It's not that there's nothing there. There's zeros, there are ones, there's numbers. That means for this example then, we did pi over 1, which is pi. Okay? So just to justify, I'm a little cut off, right? So let me pull that back on the screen. A bit better. Okay. So there we are. Now we're still going to find a quarter period. So this is going to end up being pi. I promise. You'll see. then that makes this 2 pi. So a quarter, 1, 2, 3, 4. We still have 4 spaces that we're looking at up here. Look, the first quarter, second, third, and fourth. So they're not Q for quadrant, it's Q for quarter. A quarter of what? A quarter or a fourth of the period. Okay? I know that some people are saying, but wait, a quarter is like 25. And then I asked them, out of what? 100, 25 out of 100, I promise, is 1/4. Okay? And it's always going to be a quarter. 1/4 of the period. The word of means multiply. So it's 1/4 of pi, which is pi, or 1 pi, over 4. It's a 4, not a y. It's a little curvy. There you go. Then h is 0. This moves 0 units left or right. All right. 0 is where you start, but we're going to find a common denominator. I'm going to multiply that on top and bottom by 4, because we're multiplying by 1. 4 over 4 is 1. 0 pi over 4 still though. And then I'm going to add 1 pi over 4 until I make my 9th spot. So I'm doing this 8 times instead of 4. First spot's done. Keep adding 1 to what? The numerator. Adding fractions, not that bad. Keep adding 1. So this is 1 pi over 4, 2 pi over 4, 3 pi, that's not pi, 3 pi over 4, 4 pi over 4, which is, like I said, pi, 5 pi over 4, 6 pi over 4, which also reduces, so does that one. We'll talk about that in a second. 7 pi over 4. I keep writing 4 instead of pi. No one else? And then, technically, I guess, if we're going to go that way, 8 pi over 4. The ones that reduce are, that is really going to come down to 0. This is hold on. I'll deal with it. His lamb doll is inside of my doggy backpack thing I wear to carry him around. He wants Lammy out with him. So those are all reduced. And everything's labeled there. We are still going to put 1 and -1 on the y-axis. I didn't label my x and my y. There we go. But unlike sine and cosine, we're not going to put the 1 and -1 too high. And kind of unlike cosecant, secant, we don't want to put the 1 and -1 too low, or whatever number they end up being, depending on the a value, of course. So I'm going to put it, more closely aligned with the secant and cosecant style. So here's the 1. Here is -1. So if you think you're a little fuzzy on tangent and the answers for tangent going around the unit circle, you might want to go back to the video where we went over tan, the meditating man, because you need to know where tangent is 0 and where it's undefined. It really, really, really makes a big difference. And if you don't know these things, it's really going to mess you up and your graphs are going to be all sorts of wrong, okay? So you want to pay attention to that. Another thing you might want to pay attention to, you need to remember where tangent's positive and where tangent's negative. So as it relates to the quadrants, so this is kind of drawn all over. I'm just going to go right here. This is quadrant 1, 2, 3, and 4. Tangent was positive in quadrants 1 and 3. And tangent's negative in quadrants 2 and 4. The same is true as it comes to positives and negatives. The same is true for tangent and cotangent. They're both positive. You're thinking one thing and you say another. I was like, did I say what I was thinking? So they're both positive and negative in the same place. But since they're reciprocals, the places where, gotta watch how I phrase it, the places where tangent as a fraction, ignoring the negative, is smaller on top and bigger on bottom, so less than 1 but bigger than 0 if it's positive. Cotangent will be larger than 1 and vice versa. So wherever tangent's larger than 1, cotangent will be smaller than 1. We'll deal with that when we get to cotangent though, but planting those seeds, you know? So let's make our way around, shall we? I'm just going to do a little color coding here. I'll try to be consistent for these as well. Okay. Tan, the meditating man, he sits there meditating and he's got his hands like this meditating. What did this help us remember? That tangent on the sides at 0 and pi and 2 pi. On the sides, tangent is 0, okay? So at 0, at pi, and 2 pi. I'm just going to color coordinate a little bit. Next, what else did we talk about in the story of Tan, the meditating man? We said he's meditating, he's just thinking about life, and he's saying all of his thoughts in his mind, everything above him, you know, he cannot define it. There's no way to possibly define all this. And he's sitting at a mountaintop, and he thinks of the people below him, and he's like, I can't define all these people down on earth either. So he says that they are just undefined. He cannot define them. When you have something undefined and you want to put that undefined thing into graph form, put it on a graph. How do we do that? Think of secant, cosecant. We included an asymptote. So at top and bottom with that, pi over 2 and 3 pi over 2. Undefined. So we're going to draw in a vertical asymptote. The vertical asymptotes represent a type of discontinuity known as an infinite discontinuity. We call it an infinite discontinuity because typically the branches of the graph, as they are approaching this vertical asymptote, I say approaching because they can't get there, you can cross horizontal asymptotes. Those are asymptotes for different reasons, but you will not touch a vertical asymptote when, especially if it's coming from the fact that the function is undefined. So it will never, ever have a graph there. However, as it gets closer and closer and closer, it's kind of sliding, shooting straight up or straight down, and it's going up towards positive infinity or down towards negative infinity. So it's an infinite discontinuity. So undefined equals undefined. Now, we said it's positive in quadrant 1 and quadrant 3. How is that going to relate to the picture? Well, that relates to the picture in the sense that here's quadrant 1 really. Look, 0 to pi over 2. If it's positive, you're going to have graph up there somewhere. Same over here. We're going to have graph up here. That's where the graph is going to happen. Then it's negative between pi over 2 and pi, and it's negative between 3 pi over 2 and 2 pi in those spaces. So what does that mean? Well, my output, my graph, will happen beneath my x-axis, there and there. So if you need to give that some thought. You, by all means, don't need to do any coloring there. I'm showing you to kind of help you piece together if you were doing process of elimination in some way to figure out a graph. These are little pieces that might help you. Now, here, what does tangent equal at these 4 spots? We said it either equals 1 or negative 1. Being that I already kind of marked this up in yellow, it's a little easier to tell where it equals each thing. Sorry, it's so smudgy. I had like the whiteout tape there and the orange highlighter and black pen. Pretty yucky. So we're going to have this positive 1. Tan is positive 1 at pi over 4. At negative 1, it's negative 1. Or at negative 1. At 3 pi over 4, it's negative 1. At 5 pi over 4, which is this one right here, it's positive 1 again. And at 7 pi over 4, it is negative 1, so somewhere over there. So I suppose I can just throw a little blue on those. Okay, so this is going to be 1 or -1. And it's kind of on you. You got to know which is which. It's really, those answers don't change for cotangent either, so take a little time and memorize it. Equals 1 or equals -1. All right, now for drawing this graph, the pieces of it, the way that some people were trying to say that cosecant and secant has the little parabolas, and I was like, those aren't parabolas. They don't have a parabolic curve. Sure, they look like kind of parabolic, but you know, they're little U-shaped guys. This graph kind of looks like, but it isn't, but it kind of looks like the cubing function, which is more like that broken parabola, like when the arms fell down. So if we draw that from here, we're going to start there. These points, the orange and the green, the orange and the blue are points that we are at. We're going to go here. It's concave up the entire time. And you're going to go up, 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 but you're going to get closer and closer to that pink asymptote. So the lower you make, the closer together you make your 1 and -1, the more like you could kind of do the scoop more like that. And I'll show you that in another example. This piece is concave down. So the orange points are going to act as points of inflection, where our concavity is going to flip from either concave up to concave down or whatever, depending on the graph, okay? And then this piece is really another one of this right there. Okay? So what is one period of this? One period of this, I'm going over it in purple, goes from, say, 0 until pi. I just traced over it in purple. So how many periods did I draw, or how many cycles did I draw? 2. There are 2 cycles in this picture, but I'm showing it to you between 0 and 2 pi, because that's how we're going to graph it. That's how, you know, a lot of different worksheets will do it that way. Textbooks will do it that way. They'll draw 2. And I feel like this is kind of naked, and it's a little hard for people to really wrap their mind around what's going on. Like, maybe you think this goes back up. Maybe you think this comes down. So you need to see the whole squiggle, you know? And you can kind of see it looks like a little bit like a cubing function, and it is going up, okay? It is going up. When we're done with all 6, I will point out that if you're ever trying to like remember which is which, the 3 that start the letter C at the beginning point of the positive parent function, they're all going to look like they're going down at first. So if you kind of look over your parent functions, cosine, cosecant, cotangent, when we get to it, you'll see that at 0, as we move to the right, they're going to look like they're going down at first. But we'll talk about that, like I said, in the future. As for the domain and range for this one, the domain, I'm going to wait and kind of talk about that later. But the range is all real numbers from -infinity to infinity. It goes up and down forever. So that right there is the tangent parent function. And if you could figure out the cotangent parent function, I mean, I think that would be pretty amazing. Go you. So, you know, if you feel a little adventurous, I would definitely recommend you try it. But I'm going to do an example right after this, and hopefully you're able to follow. And then I will give you one to try on your own afterwards. All right? So take good note. Period is pi over b now, not 2 pi's. When you're tan, it's summer, you're outside, got to cut back on the pi. Only 1 pi, you know. But we still find 1/4 of the period, but we're going to keep going, and we're going to do 2 full periods. So you tan in the summer, 2 full months. You're looking at July and August. I don't know. I'm trying. Okay. So I had mentioned that here, opposite over adjacent, the opposite, when you're on this little piece before pi over 4, the opposite side, which is here vertical, and the adjacent side, the opposite will be smaller. That means that your fraction will be less than 1. And here's the 1, and it's less than 1 right there, you know? And then here, my opposite side is going to be bigger than my adjacent. So my opposite over adjacent will be bigger than 1, and it is. It's going up. And how grand can that variation be? Well, quite grand, because you can go up, 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 up forever. So on and so forth. Same idea. That's why we'll have these pieces, before the 1 and after the 1. So I just wanted to point that out because I did bring it up earlier, but I didn't kind of elaborate on how that connected back to the graph. So I just wanted to come back in and add that little tidbit of info to the video. So if you stay tuned till the end, thank you. You're the best. If this is clear, if you think you know the parent function and you could work to memorize, learn, understand it fully, thumbs up. If you need tons of support on this, thumbs down. And I really appreciate it, so I can kind of monitor how you're feeling. I don't know who gives thumbs up or thumbs down. It's totally anonymous, so knock yourself out, go crazy, and I hope you have a really nice day.